So we'll continue to discuss on this ARM architecture. So we're going to look at the data processing source to variation. So we did some before, but we'll just start from here, immediate one. Okay, so data processing instructions. Now we're going to look at the immediate one. Let's say we have add R0, R1, and 42. It is easier to go through this sequence to going from assembly language to machine language. So what is opcode for the data processing? 00. And the CMD for add 0100. So you need to use your handout. We have an immediate, so I has to be equal to 1. And I don't see S, it's going to be 0. And then condition for all data processing instructions, it's going to be what? 1110. And then we're going to fill in RD, the destination, and should be the first register right after the instruction code. So R0, so it's going to be RD is 0, and RN is right there, which is 1. 42 is smaller than 255, therefore we can fit it in here, 8-bit. Rotation is going to be 0, and you just need to put 42 there. When we convert into hexadecimal, group them into 4 bits, that is 0x E28100028. Since we can fit this 42 within the 8-bit, now we have 42 and no need to do the rotation. Now if it is a larger than 8 bits, then we need to use rotation. So the ROT, this is something you want to write down. The ROT values that we're going to put is ROR divided by 2. What is ROR? Rotate right. So we need to figure it out how many bits to the rotate right and divide that number by 2. That's going to be ROT values within 4 bit. If ROT is 00, then this immediate 8 is A, B, C, D, E, F, G, H. Right, as an initial number. Now, if we do ROT1, so we have to have 2-bit rotation to the right so that we can have the value of ROT as a 1. If we did, we have GH in here. If we do 2 as a ROT value, that means 4-bit rotation to the right, right? Because we have to have a 4 rotation right. 4 divided by 2, we can get ROT as a 2. Therefore, if we do it, we end up getting this. And all the way down to 1111 is this. Our first example, add R0, R1, decimal 3008. Obviously, there's no way we can fit this 3008 into 8-bit, right? What's the binary number for this? 3008 is 101111000000. So we want 1011 11000000, and I use 0b as a, again, just like a 0x. 0x is a hex, last letter of hex. 0b is a binary notation, or use the parentheses and then subscript 2. So this is 3008. I put it in here as a 4 binary number bits at a time. So 1011 1100 0000. That's what we want. But we have only 8 bits. Therefore, I'm going to just use this first 6 bit to the bottom. We can start from here. That's the 8 bit. And then we need to rotate to the right. So this is the start point. This is 3008, which is 1011 11000000. We cannot fit it into 8-bit binary number. So what I'm going to do, I'm going to take this portion, first 6-bit of most significant bit, into 8-bit in our portion of the immediate value. Now we need to figure it out. How many rotation do we need to do to get to this? So we start with this. Now we're going to rotate. ROT value 1 means what? Rotate to the right by 2. So now we have this. If I rotate 4, ROT value is going to be 2. Now it's going to be 4. And we can all do the last one we saw in the previous 1111, which is 15, the largest value we can get as a ROT. If we take this, we end up getting this. That's why we are using 4-bit ROT values. If I go one more, it's going to be the original. So we just need the 4 bits to rotate whole 32-bit of the constant register, but we have to rotate 2 bits at a time. Hey, Dr. Kim, if we want to rotate 3 times, is it possible any odd number? It's not possible. We cannot do that using ROT. Then we need to extra instructions to push back or take it back, or we need to move that. Since this is 1111 is this guy, what about 1110? 1110 is to the left by 2 bits from here, and then 1101, which is what we want, that is 1101. Now, if we keep doing this rotate right, it's kind of confusing and you need to create this table. However, we know from here to here, we can rotate to the left by 6-bit. If I push this guy left by 6-bit, it's going to be this. Even though it requires rotate right, it's much easier to rotate left. And how many bits of rotate left? It's going to be 6-bit. But now we know rotate left by 6, meaning rotate right by 32 minus x. So rotate by 6, meaning rotate right by 26. And then root 26 divided by 2, 13. That is the same number we have. The question here is we start with 00101111, but what about starting with 10111100? Can we do that? Yeah. We're gonna do what? In this case, rotation left by 4. So our ROT value is gonna be ROR by 2, which is 32 minus 4 over 2. That is 14. Then you can put this into here, and instead of 13, we're going to put 14. So 1110 in the ROT. Then we get exactly the same result. Hey, Dr. Kim, what about this? If this is the case, we'll leave 5 zeros and rotate left or rotate right by odd number of bits. That's not going to work. Let's do this. This time, subtract R2, R3, 0x, FF0. Opcode is 00. COMD is a subtract, 0010. Immediate 1 and S set no. And then condition 1110, RD 2, RN 3. Now, what we want is FF0, 1111, 1111, 0000. We can start with this. So put this 1111, 1111. Now we need to figure it out how many rotate to the right, but instead of using rotate to the right, it's easier to rotate to the left. So in this case, rotate to the left by 4. That means 32 minus 4, which is 28. Rotate right by 28. So our ROT value is 28 divided by 2, 14, 1110. Yeah, we have this, but we want this. So we need to rotate to the left or right. We need to rotate to the left by 4, which is same as rotate right by 28. After we put that into hex, so it should be this. So you want to copy that down as well. Make sure you know how to combine 4. It's not very straightforward because it's separated by with the different units. You need to be careful combining 4 bits at a time. And when you combine them all, it should be divisible by 4, right? It's 32-bit. So last 2 should be F and F. But in the middle, it could be different numbers. The registers, if you have another register and we need to shift that content of register before we add, subtract, or anything, we can have that. That's the third variation from data processing instructions. And logically shift to left is 0, 0, logically shift to right, arithmetic shift to right, and rotate right. Those are the 4 different ones we can fit in here. Why we don't have arithmetic shift left in here? Exactly. So arithmetic shift left is exactly the same as logical shift to left. Then what is the difference between logical shift right versus arithmetic shift right? So logically shift right, we are shifting to the right by, let's say, 2, if we have 1101, if we have logically shift right by 2, so 110111. And these missing 2 bits always for the 0 for logical shift. However, arithmetic shift right by 2, we have 110111. Any empty spot, we need to copy MSB most significant bit and copy so that we can keep the sign of this number. It was a negative number, now it's a negative. If it was a positive, which is 0, then we copy down 0, so still we have a positive number. So add R5, R6, R7 is just simply add up CMD is 0100, condition is 1110, R5, R6, R7, those are the RD, Rn, and then third one is the Rm, and that's it. But if you have LSR2, we have a up as a 00, and then CMD is 1100 for OR, and immediate 0, S0, COND 1110, RD 9, RN 5, RM 3, and then shift amount is 2, SH, shift LSR is 01, and then we have a 0 right there. And then our hexadecimal number for this instruction, E1859123. When we have a register shift, we have R10 and ROR, R12. We have all of this, and then RM is going to be R10, and then RS1100, which is 12, and then 0, SH is going to be 11. Major difference between this guy and this guy, we have a 1 in here, then this is 0. In this format, when we decode from hexadecimal or binary to assembly, we need to look at the 5th bit from the lowest bit. Let's move on to memory. In memory instructions in our class, we're going to look at these 4, mainly focus on LDR and STR. This is the typical instruction format. We're going to have different variation of the funct and source too. First of all, the funct, we have I bar, P, U, B, W, and L. All of this, we should be able to find exact values from handout, our cheat sheet. And for memory, our opcode now is 01. Data processing opcode is 00. Memory opcode, we have a 01. This is the I bar. I is the immediate. So if it's immediate, we need to put 0 this time. If it's not immediate, we need to put 1. So it's the I bar. Please note on that, it's not just I. It's the I bar. This portion is a 0, that's the immediate. This portion is 1, it's not immediate. It's the opposite from the data processing. And this kind of example, LDR R1 is our destination, and then offset plus R2 base address, that's the target address we want to go into main memory, bring it into register R1. And for LDR STR instruction, these are the variation of the different ones. So we could have a positive number, we could add the negative number, we could use whole content of register, we can have a negative of the register, and shift as well. We have either immediate 12, immediate values only, or immediate with another register or with the shifting. There are 3 different modes to find the exact memory address. The first one is offset. That's the most typical one. If you have kind of the number, it's an immediate number. So we need to add these 2. That's the location of the memory. Go there, grab the content of my memory, put it into R1. Very straightforward. And we've been talking about this many, many times. If you have an exclamation mark at the end, then it is what we call pre-index. So we're going to have memory location R5 plus this number, but we're going to update the value R5 with the new value. That's not happening in here. We want update R5 values. And then post-index, as we just had the bracket with only in the middle, we just use R1 only. Whatever the contents of R1, we're gonna use that as a memory address. And the later number, we're gonna add that to R1. We update the contents of R1. So as you can see, all these three, whatever we have inside of the bracket, that's the one we're gonna use memory address. Make sense? Inside of the bracket, that's how we calculate the memory address. R2 plus 4, R5 plus 16, or R1 only. We can figure it out the value of I by looking at the instructions. So these are all I. I bar should be 0. I bar should be 0 because immediate values. But here, there's no immediate value, right? So I bar should be 1. L and B, 0, 0, store, 1, 0, load. And 0, 1 is a byte, 1, 1 is a byte. So if we have a byte for load and store, the B bit is gonna be 1, otherwise 0. And the immediate offset, we talked about it, U value, U equals to 0, we need to subtract, U equals to 1, we need to add. And then those are the indexing mode, 0, 1 is not supported, 0, 0 is a post-index, 1, 0 is offset, 1, 1 is a pre-index. So you don't have to memorize any of those. We have a chart. You should know how to use them. That's all.